Hello there, everybody. This lesson starts us off on our journey for finding volumes. This first lesson is about finding volumes using cross sections. So we've got cross sections that are semicircles in this first example, semicircle, half circle. The semicircles are perpendicular to the y-axis. Here's the y-axis. Here's the x-axis. They're perpendicular to the y-axis. And the base of this solid, if you were setting it on a table, the part that's in contact with the table is bounded by y equals x squared and the line y equals 4. So that's the base of the solid, and they're semicircles coming up from there. Okay, so the volume of each of these cross sections, like if you think of these kind of like our Riemann sums or the rectangles that we talked about when we were doing area, these have if you could think of these as having a little bit of a thickness, that thickness tells you what dx or dy is. And the volume of each of these cross sections is just the area of the front of the cross section times the thickness. Now the area depends on the shape that you have. In this case it's a semicircle, so we'll use a specific formula to find that area. But if it's a square or an equilateral triangle, whatever it is, the area of that cross section times the thickness gives you the volume. Now I put D here because for this one, that thickness is a y quantity, so we would integrate dy. Sometimes the thickness is an x quantity and we would integrate dx. But this d whatever is the thickness of the cross section. You multiply that by the area to get the volume of a little sliver of the solid, and then the integral adds them all up. And of course you have bounds here as well. But this is kind of the general formula for finding volume using cross sections. Now, whatever this is, if this is x, then our bounds are for x. If this is a y, our bounds are for y, and we'll talk more about that in a second. But that's kind of generally how it goes. So let's take a look at this first example here. Again, semicircle cross sections perpendicular to the y-axis, bounded by y equals x squared and y equals 4. I've drawn a cross section down here. Let's set up our integral here. We said that the thickness here of one of our cross sections. Let's just draw the rest of it here. So there is kind of like a lemon slice you would see in some iced tea or something is kind of what it looks like if you get in a restaurant. But the thickness of that cross section, that's dy. So we know that we're going to be integrating dy here. Now that means our bounds are for y also. Okay. So we know we're going from y equals 0 to y equals 4, so we can fill that in. Now the rest of it is the area of the cross section. That's why I've drawn this here. The area of a semicircle or a half circle, well, a whole circle is pi r squared. So a semicircle is going to be 1/2 pi r squared. Okay. So we need to know radius. Now the radius of our semicircles here, that is an x coordinate of a point on this parabola here. So r equals x. But we can't put, since this is dy, we need this in terms of y. So now this is an x coordinate on this curve, y equals x squared, and if you solve that for x, you get the square root of y. So our radius is really the square root of y. Okay. So if you put that in there, we get 1/2 times pi. Now the square root of y squared is just, I'll write that in there, square root of y squared is just y. So this is 1/2 pi. Y is the area of our semicircle. We put that here, and we've got our integral that we can evaluate to find this volume. This particular antiderivative is going to be easy. It's going to be, let's see, pi y squared over 4 from 0 to 4, which is, let's see, pi times 4 squared over 4 minus pi times 0 squared over 4, which is 4 pi. And there is our volume. Let's take a look at another example. Here we've got cross sections that are equilateral triangles, and this time perpendicular to the x-axis. Here's the x-axis. I've drawn a couple of those equilateral triangle cross sections. The base of the solid is bounded by the line y equals x plus 1, the x-axis, the y-axis, and the line x equals 3. So there's the base of our solid. Okay. Now let's see if we can find the area, or the volume of our solid. Now the thickness of our cross sections, that's an x quantity this time. So our thickness is dx. So I know I'm going to have dx here. That means our bounds are for x. We're going from 0 to 3 this time. And what goes in here is the area of our cross section. Now, a triangle area is 1/2 base times height. Now, the base of our cross section, the base of our triangle, is a y quantity, but we need it in terms of x, and y is x plus 1. So that's the base of our triangle. Okay. So it's going to be 1/2 times x plus 1. Now the height is this. Now, since this is an equilateral triangle, from here to here, that's half of our base. So that's going to be x plus 1 over 2. And again, it's an equilateral triangle, so this is 60. That means this is 30, since this is 90. We got a 30, 60, 90. Now you can, well, I wouldn't use sine, cosine, and tangent to do this if I were use because of the x's here, but the shortcut, which I've taught in geometry, obviously 100 times, you multiply the short leg by the square root of 3 to get the long one. So this is x plus 1 over 2 times the square root of 3. And that's the height of the triangle. So we've got x plus 1 over 2 times the square root of 3. 1/2 base times height. And there is the area of our cross section there. So we just put it in here, x plus 1 over 2. Let me move this over. Times the square root of 3 dx. And there is an integral that gives us the volume of our solid. This particular one, I would plug in my calculator. Doing it analytically is quite labor intensive. Your assignment is on page 406. It's number 1 through 3. The directions don't tell you to find the volumes, but I'm changing the directions a little bit. I want you to find the volumes in numbers 1, 2, and 3. Good luck. Have a good day. Bye.